Hello.
Madam, please start.
Okay. Thank you, madam. Shall we wait for another 1 2 minutes or start right now?
Just then wait for 5 minutes. Actually,
At least 5 till
2 3 minutes. Just
2 2 minutes. At least we can wait
yes,
because
yes.
right now number of participants is very less. A very good afternoon to all of you present over here. I, Rochita Ghoshajra, on behalf of MCKVIE Institute of Engineering and on behalf of the organizing committee of ATAL Academy 6 days online FDP on quantum edge intelligence, welcome you all in the today's session. This program is organized by the Department of Computer Science and Engineering of MCKVIE Institute of Engineering. Today is the last day of this FDP. And right now, we are going to start session 11 of this week-long program with a lecture on quantum computing and noise mitigation. Today, we have with us Dr. Ritajit Majumdar. He is a research scientist at IBM Quantum, IBM India Research Lab, and he also serves as a visiting faculty in the Department of Computer Science and Engineering at University of Calcutta. He received his PhD in computer science from Indian Statistical Institute in 2022. He has completed his BTech and MTech in computer science and engineering from University of Calcutta in 2014 and 2016 respectively. Dr. Majumdar has contributed extensively in the field of quantum error mitigation, algorithm optimization, and quantum system design with several published papers in reputed international journals and conferences, with several patents filed in these areas. He has also been recipient of these prestigious awards like Fulbright Nehru Doctoral Research Fellowship at IBM Thomas J. Watson Research Center and Doctor's Reserve Allocation Award from US Department of Energy National Energy Research Scientific Computing Center. Through his academic and industry roles, Dr. Majumdar continues to bridge the cutting edge research with practical advancements in quantum computing. With this brief introduction, may I now request Dr. Majumdar to deliver his lecture on this topic of quantum computing and noise mitigation.
Thank you, ma'am, for the kind introduction. And I'm very happy to be here. Thanks a lot for inviting me to this FDP. Yeah, let me share my screen.
Sir, is it possible to switch on your camera, please?
Okay, yeah, sure. Yeah, so is my screen visible?
Yes, sir, it is.
Okay. So yes, today we are going to discuss.
Sir, one request, can you switch on your camera, please, for 1 or 2 moments?
My camera is switched on.
Yes, it is
Uh,
on.
That has switch on.
But it is not coming in my screen. Okay, let me check.
Yes, it's coming fine.
Fine.
Yes, yes, right. Okay, thank you, sir. You can continue.
Sure, sure. Thanks. So, okay. So what we are going to discuss about today is this fighting with noise before error correction, suppression, mitigation, and beyond. Maybe we won't go into the beyond part, but if we have time, I'll just touch upon what I mean by beyond. But we'll talk about suppression and mitigation. I remember actually there are many jokes if you have heard of quantum computing. Like one of my very favorite joke here is that someone comes and tell is that I have a quantum computer now, and the other person says that yeah, that's great, but your quantum computer is broken in every possible way simultaneously. So that's precisely the scenario of quantum computing today. We already have sufficiently large quantum computers to the extent that if there were no noise in the system, we would have already been doing stuffs that are impossible for any classical methods to do. But we are restricted by noise, so we have to deal with it, and that's what we are going to discuss here today. Um, this is kind of the agenda that we will look into. I'll just first introduce certain things about this, and we will mainly look into three types of error mitigation: zero noise extrapolation, twirling, and measurement error mitigation. But once more, this is something I would definitely urge you all, is that it's actually a lot, and the goal that I will have today is not to just complete everything that I have written here, just bombard you with everything in the slide, but we will try to walk the steps together. And whenever you have any questions, I'll definitely try to pause and take any questions in between. But even if I am not pausing, if you have any questions, please stop me and ask questions. um, we should be ending this not by telling everything that is there, but whatever we are able to cover, you should be able to go back and apply that in whatever research that you are doing in quantum. So with that, let's start by our introduction. So let's ask this question, that what can we do with a quantum computer? It seems a very naive question, like you have already been doing, maybe some of you are already working on quantum computer for quite some time. If not, this has been some week-long FDP or something. So this is the last day of the FDP. You have already heard from other speakers, and I am starting by saying what we can do with a quantum computer. But this is kind of going back to the basics and answering the basic question gives us some insights which will be very, very important for error mitigation. So what do we do with a quantum computer? We have some qubits, we have a quantum circuit, and then we measure. That's all we do, right? Now, when we measure, we know that quantum systems are probabilistic. So if I create the same circuit, even if there is no noise, forget about noise, even if there is no noise, when I have the same circuit, if I measure it 100 times, I am not always guaranteed to get the same outcome. Of course, there are certain algorithms where the outcome is guaranteed in the absence of noise, but in many algorithms, that is not the case. So if you measure the outcome, you will get, say, outcome 1 sometimes, outcome 2 sometimes, and so on. So in other words, we can say that we will obtain a probability distribution if we run the circuit, say, n times, and this n times is called shorts. It's just a terminology that if I run the circuit n times, that means if I do n shorts, then I will end up having a probability distribution out of this. From this probability distribution, what we can do, even we do this in classical computing, we can calculate the expectation value of some observable. So again, perhaps you already know, just for the sake of completeness, what is an observable? the immediate answer would seem like you are going in cycle. Observable is something that you can observe. So what that means is that, say I have a quantum system. I want to find out the energy of that system. I want to find out the momentum of that system. So for each of those things that I am willing to compute, energy, momentum, angular momentum, anything else, spin, whatever I am interested in calculating, I need to create an observable, that's a mathematical expression, and the eigenvalues of that observable are the possible outcomes. So when I measure the system, I will end up in some eigenvalue of that observable. So just to give you a flavor, if say when I run this quantum circuit, the outcome is some quantum state psi, then how we calculate the expectation value mathematically, we calculate this term. This is the bra psi o get psi. So we calculate this term. Physically, what we do is any observable is a Hermitian operator. So any Hermitian operator can be written down as some sums of Pauli's, weighted sum of Pauli's. So P are Pauli's here. So what it means is that we will have multiple such psi P psi term. So I can write down psi O psi as this sum over Cp psi P psi. So what I am going to do is I am going to use a quantum computer to calculate each of these terms. And once I have each of these terms, I need to multiply by Cp and do the summation that we can just do classically. So this is what we do with a quantum computer. Either we get a probability distribution out of it, or using the probability distribution, we calculate the expectation value of some observable. So here is just an example of doing that. Let's not go into this. But why am I putting so much emphasis on this very simple thing? The reason is, when there is noise in the circuit, we want to correct for the noise in general. That's error correction. That happens in classical computers also, although classical computers have very, very low error compared to quantum computers. But still, we do have many like Hamming codes and checksums and things like this. So if you are able to do error correction, then you can detect that, okay, an error is happening and I am going to correct it. So this is something that we can do. But if you are going for error mitigation, we will see what that is in some times. But if you are going for error mitigation only applicable when you want to calculate the expectation value of some observable. So think of this, if you are thinking of Shor algorithm, let's say, you want the final bit string because the bit string is going to give you the factors of the number you are trying to factorize. If you are going for Grover's algorithm, you again need the bit strings because the bit strings is giving you the element that you are looking for. Many other such algorithms exist, right? Bernstein-Vazirani, Simon's algorithm. In all of these algorithms, you need the probability distribution. You don't need to calculate some expectation value. Or quantum communication. Say I am saying something to you. I am sending you some bits, zeros and ones. You are interested in receiving those bits correctly, not in calculating the expectation value of those bits. That makes no sense. Say you are making a quantum adder. You want to add two numbers and get back that number, not an expectation value of that number. So these are many, many scenarios where error mitigation is not applicable. So this is the reason why I am emphasizing it so much, just to set the context where error mitigation is not applicable. The scenarios where error mitigation is not applicable, these are not near-term applications. We cannot factorize a pretty large number today. It is still going to take quite a few years, maybe many years, to actually start breaking RSA crypto systems at the scale where it matters. But having said that, having kind of thrown away so many things, adders, multipliers, Grover's algorithm, Shor algorithm, quantum communication, quantum cryptography, having thrown away all of those things, that error mitigation is not applicable in any of those. So where is error mitigation actually applicable? Many problems. Think of physics. there are so many physical problems where we actually need to calculate some observable. Like I started giving examples by saying that, we want to calculate momentum of the system, we want to calculate energy of a system. These are extremely important. Similarly, chemistry, we want to know, say, when two systems interact, what is the energy when they actually form a bond. This gives us a lot of information for many important problems like drug discoveries and all. So I need to know that energy there. So chemistry, physics, machine learning. In machine learning, when I run the system, I am interested in, say, some F1 value, some accuracy. These are some numbers, and I can actually construct an observable which corresponds to these things. So machine learning, optimization, combinatorial optimization, graph problems. Say I want to find out what is the vertex cover of this graph. Say I want to find out what is the size of the Hamiltonian cycle of this graph. What is the max cut of this graph? These are all some numbers. It is possible to construct an observable corresponding to those and calculate those using a quantum computer. And in all of these cases, error mitigation is applicable. So this is something very important, and there have been many papers I have seen where people kind of claim that, okay, I have a quantum communication system and I can improve this by doing error mitigation. So just be careful where error mitigation is doable, where error mitigation is not doable. So this is an example of a 127 qubit quantum computer. It's the IBM Shared Group, the name. And I remember one of my ex-colleagues, he did a poll that what do you think is the major obstacle in quantum computers today? And naturally, the answer was noise. So you see what types of noise are there? Every type of noise. If you ask that, okay, you are doing these gates, are they nice? Are they perfect? No. So there are error rates that you can see here. The error rates are given here. So these are single qubit error rates. It's named after Hadamard error, but it's just a single qubit error rate. And C naught, 2-qubit error rate. So you can see that the lighter it is, like this C naught is very erroneous. This C naught is better. This single qubit gate is better, this single qubit gate is worse, and so on. Similarly, readout. So readout error is as simple as saying that, I asked you that, okay, did you like this talk? You said yes, I wrote down no. So as simple as that. So readout error, you see that when we look into a state and we find out whether the state is in 0 or 1, it collapses. So we find out whether it's in 0 or 1. There is again some error there, and some of the qubits are very erroneous in terms of readout, while the others are pretty good. So noise is a major obstacle. And what we see in the current roadmap of IBM, so we are standing here up to this, everything as you see are marked with green. So these are done. The IBM roadmap started from 2016. We are standing here today. It is in 2029 and beyond that we expect that error correction is going to come in. So the natural question will be then, what do you do till 2029? It's roughly end of 2025. So are you going to wait for just 4 years doing nothing? And then from 2029, you start doing stuffs? No. And this no is so confident that we often say that this kind of thing, that whenever you are doing experiments with your quantum computer, if you are not using 100 qubits, it is not quantum, it is something else. Why do we make such a statement? The reason here is, think of this. If you are just doing a 10 qubit experiment, running it on a simulator, on a quantum computer or not, the first thing is you can run it on a simulator. That means it is doable classically. That means you don't need to go to a quantum computer to do this. It is as good as saying that if you come today, or if I come today to you and say, I have a quantum algorithm for binary search. well, the reaction will be good for you. I mean, binary search is already so efficient. What are you doing with a quantum algorithm for it? Give me quantum algorithms for other problems, other important problems where classical is having difficulties, where classical is already doing great. It makes no sense to say that I also have a quantum algorithm. You know, you have a bubble sort algorithm, I have a quantum sort algorithm. These are not interesting problems. They are, of course, doable, but these are not interesting problems. So if you are using just 5 qubit, 10 qubit examples, these are doable classically. And in fact, you are just simulating them on a classical computer. So whatever it is doing, it's a quantum inspired algorithm. It's not a quantum algorithm. It's only makes sense to do quantum algorithms. It's only makes sense to do something quantum when you are going beyond the regime of what classical can already do. Otherwise, for example, I can even come and say that, you know, I am using the world's most powerful GPU to do bubble sort. Okay, so what? I mean, you can, but so what? The same question goes here. So what if you are just doing some small examples? Does that mean that you always have to start by doing 100 qubit examples? That's not doable if some of you are just getting started. Of course, not doable. We always want to start small. We always want to gain experience, start small. But this is the aim. Just like we start doing Hello World when we are in college and just learning to code, but say within just 4 years we do so great projects nowadays, in even in bachelor degrees, right? So that should be the goal, that we always want to start small, but we want to that in the next few years we are going to this regime. Otherwise it makes no sense. But having said that, what you should be thinking is that you already said that error correction is not there. So you already said that error is one of the biggest obstacles. You already said error correction is not there. And now you are saying that if you are not using 100 plus qubits, you are not doing quantum. Are there examples of people doing 100 plus experiments now, not in 2029 or beyond when error correction is there? Yes. So these two slides, and these are not exhaustive. You can see it's not just one or two examples that people has only one or two people has done. And there are examples from physics. There are examples from optimization. These are high energy physics, um, optimization, chemistry, optimization. So many things, physics, so many domains. It's not just a single domain that people have been able to do. And so many works have been done that are using 100 or very close to 100 qubits and thousands of gates. How are they doing it? So how are they doing it is via mitigation and suppression. So what we obviously want to reach is error correction. So what is error correction? In this regime, errors are detected and then corrected. If you can do this, you can suppress the error to an arbitrary low level. But it requires a large number of qubits, and there are many hardware requirements, a lot of overhead that comes into this. Perhaps you have heard of this already, but if not, that just to do Shor algorithm, for a practically useful example, not to factorize 15, but to do a practically useful example, you would need millions of qubits. That is the overhead of error correction. But today we can do mitigation and suppression. We don't really need to, differentiate between these two. But the only thing is that in suppression, no extra qubit or runtime is required. In mitigation, some extra qubit, some extra runtime is required, but no extra qubit is required. These two cannot really detect the error and correct, but they actually do some extra hardware run with some post processing to kind of mitigate the effect of noise. They can extend the lifetime of computation, but obviously, like error correction, they don't suppress error to some arbitrary low level. And we will see examples of all of this that I just discussed. So the question is how to deal with noise. But to deal with noise, let's first know our enemy. If we want to fight with the enemy, let's know the enemy first. So what are the different types of noise? Well, don't even ask to write down. There are so many different types of noise, maybe many types of noise which even I don't know about. Depolarizing, over rotation, T1, T2, crosstalk, state preparation. So if so many types of noise are there, then to fight with it, we need multiple methods as well, right? So to fight with T2 and crosstalk, we have dynamical decoupling. Maybe we won't go into detail of dynamical decoupling today. To fight with all these other types of noise, we have something called twirling. Twirling doesn't really mitigate the effect of noise, but it kind of makes the noise more systematic. Once the noise is systematic, we can apply measurement error mitigation for this particular type of noise, SPAM, or there are different types of error mitigation techniques like zero noise extrapolation, probabilistic error amplification, etc., which is applied on top of this. So this is kind of not either or. It kind of goes this and this, twirling and zero noise extrapolation and dynamical decoupling. All of them goes together. So we will start from the outside, and as much as time permits, we will start going towards the inside. So before I start with zero noise extrapolation, if there are any questions or anything, I'll be very happy to take. Okay, if not, let's again go back to this. Right. So let's start with zero noise extrapolation, and you will see that this is a very, very simple method. So first, we will assume that the noise in the circuit can be parameterized by some value lambda. Let's not ask what is lambda, what do you mean by what is the physical interpretation of lambda. We won't ask this question. We will just say it is some mathematical thing. I don't know what that thing is. It's some mathematical thing that characterizes the noise in the circuit. How does it do it? We will see how it does, but for now we won't even care about this. Let's assume that we can parameterize the noise in the circuit with some lambda 1. Now, this lambda 1 is called a noise vector. Now I create a set of noise vectors, increasing order. Now, for each set of noise vector, I will create a circuit that corresponds to that noise vector. I am not answering how. We will answer how. But this is the protocol that you create a set of noise vectors, you create circuits that corresponds to those noise vectors, and then you calculate the expectation value for each of those circuits. So this is the expectation value corresponding to the original circuit. This is the expectation value corresponding to some higher noise circuit, and so on. And what is happening here? These circuits need to be functionally equivalent when I do this. So now I am getting different data points. So see, lambda 1 is some measure of the noise associated with the original circuit. Here, I have a functionally equivalent circuit, but somehow I have increased the noise of that circuit. So this expectation value will be even worse than the original expectation value. Similarly, lambda 3, I have kind of taken a functionally equivalent circuit, but increased the noise in the circuit even more. So this expectation value will be even worse. But what this is giving me are some data points. So what I can now do is I can fit a curve and then I can extrapolate it. And this extrapolation, this E star, gives me an estimate of what the expectation value should have been if my circuit didn't contain any noise. And this is again very important. Again, a lot of people confuse this. So again, putting a lot of emphasis here is error mitigation does not reduce the noise in the circuit. It doesn't reduce the noise in the circuit. Rather, it gives an estimate of what the expectation value should have been if there were no noise in the circuit. So this is a very, very important thing to keep in mind. And this is, as you can see, this is a very simple idea of how to do it. Just get different data points, fit a curve, extrapolate it. The question here is then how do we, the question here is how do we get this data points? What are these lambda ones? How do we create different lambdas? How do we build the circuit that will have noise, a bit of higher noise, but will be functionally equivalent? So all these questions are here. Let's answer these questions now. So what we will look into, there are two types of mitigation, or there are two parts in mitigation if you think. This part where this is the noise factor corresponding to the original circuit, this is some increased noise, the circuit is functionally equivalent. So this is called amplification. The noise is somehow amplified. And then this is called extrapolation. There are two steps. Amplification, as you can see, is quantum. These are quantum circuits. Extrapolation is classical. It's just fitting a curve and extrapolation. So one method of doing that is something called gate folding. We know that, let's see that, take an example circuit. We know that in a quantum computer, each of these gates are unitary. So if it is a unitary, then its inverse always exists, and the dagger, so the complex conjugate dagger, is its inverse. That's the definition of unitary operator. So if I replace this U1 with U1, U1 dagger, U1. So see, these two is identity. It is effectively U1. So this single gate and these three gates, these are functionally equivalent. But the obvious thing is these gates are noisy. If this were not noisy, then this circuit and this circuit would have given me the same outcome, because this one gate and these three gates are functionally equivalent. But this circuit is noisy. So when I replace one gate with three gates, the noise is amplified 3 times. Previously, only just looking into this gate, previously the noise was only coming because U1 was applied. Now the noise is coming 3 times because U1 is kind of applied 3 times. U1, U1 dagger, U1. It's kind of applied 3 times. So the noise increases 3-fold. Now I could have replaced this, say, 5 times, 7 times, 9 times, whatever. Whatever I do, the first part is identity and it only remains as the original gate. So this is the example that I have given here. This is called lambda equal to 3, noise factor 3. If I repeat it 5 times, it will be lambda equal to 5. If I repeat it 7 times, lambda equal to 7, and so on. So we replace a gate U by this type. And then this will look a bit of mathematical. Let's not worry too much about the mathematics here. But what we can do is, now this is lambda equal to 1. This is lambda equal to 3. Say similarly, I have 5 times, repeat the gates 5 times. That will be lambda equal to 5. So then what I can do is, so this point becomes 1, this point becomes 3, this point becomes 5. I will calculate the expectation value by running it on a quantum computer. So done. Now I will fit a curve. How will I fit a curve? So this calculation of expectation value stuffs are given here a bit mathematically. Let's not worry about those. So how do we fit an extrapolator? If we think of a Pauli kind of noise, a Pauli noise is given like this. If my original quantum state rho, the way it gets distorted because of noise is with 1 minus p probability, it is still rho, and the rest is the error term. So if this is for a single gate, if there are n gates, this will go down 1 minus p to the power n. So it goes down exponentially. So naturally, the extrapolator that we expect is exponential in nature. But again, if my p is very small, or if my circuit is not sufficiently large, then we can actually say that, okay, if I do a Taylor series expansion, then we can say that, okay, a linear extrapolator is a good enough approximation of that exponential extrapolator. Or if it is slightly deep, we can say, okay, a quadratic extrapolator is a good enough approximation of the exponential extrapolator. So if it is a small circuit, we opt for linear. If it is slightly bigger circuit, we opt for quadratic. If not, we opt for exponential, which is the natural nature. You can ask that, okay, you already said that the actual nature of the circuit is exponential. The nature of this noise is exponential. So why go for linear, quadratic, and all of those things? Why not just have exponential? Because in practice, what is seen is exponential extrapolators are highly unstable. You end up with a very large standard deviation if you do exponential extrapolation. So wherever possible, we always try to use linear or quadratic extrapolator. When the circuit becomes very large, where linear or quadratic or even cubic, these are not sufficiently good approximations, we have to go to exponential. But if given a choice, we would always go for lower degree polynomial. Lower the degree, the more stable it is in general. There are certain good practices when we apply digital zero noise extrapolation. So the first thing is the example that I showed here, every gate is folded. Every gate is folded. But in practice, what we do is, you can see that when I fold every gate by 3 times, the depth of the circuit increases 3 times. If I do it 5 times, the depth of the circuit increases 5 times. So if this is already a sufficiently deep circuit, and then I increase the depth 3 times, 5 times, highly likely that we will end up with white noise at the end. It's just some random white noise, and then there is no signal. If there is no signal, if it is just white noise, then extrapolation will not give me anything legitimate. It will just be a random extrapolation, right? So the first thing that is done, in general, 2-qubit gates are way more noisy than single qubit gates. And when I say way more noisy, they are often 10 to 100 times more noisy than single qubit gates. So the first approximation that is done is, compared to 2-qubit gates, single qubit gates are almost noiseless. This is the first approximation that we do. So let's only fold 2-qubit gates. That way, you restrict the increase in depth to some extent. Mark my word when I say that this way, you restrict the increase in depth to some extent. As I said, even before going into ZNE, that we want to run circuits which are of 100 qubits, thousands of gates. That's where quantum is useful. So if quantum is useful there, here is an example that say that the 2-qubit depth, that means you forget about all the single qubit gates and you calculate the depth only considering 2-qubit gates. Say the 2-qubit depth of the original circuit is 20 and I do lambda equal to 5. Now my 2-qubit depth becomes 100. So perhaps it is already too deep to convey any reliable signal, even after doing this approximation. So what we do, the solution is partial folding. In partial folding, what we say is that we have fractional noise factors. And this is why I kept saying in the beginning that let's not put a physical meaning to lambda. So when I say lambda is a fraction, say 0.2, it means you take 10 2-qubit gates, randomly select 2 out of them and fold them. So what it does is it restricts the increase in depth due to folding, and this makes ZNE useful for very, very deep circuits when you do something like this. And the first utility paper that was done actually used this kind of folding. And this kind of folding, they were able to go up to a 2-qubit depth of 60. The original circuit's 2-qubit depth was 60. I was given an example with 20 here. But even for the original circuit, the 2-qubit depth that they did was 60 with 127 qubits. So partial folding is extremely useful here. There are certain cases where ZNE doesn't work. So say as, okay, sorry, I need to change this, as P tends to 1, sorry. If it is a depolarizing noise, As P tends to 1, the system tends to a maximally mixed state. So a maximally mixed state is something where all information is lost. So it's like you have no information left. You are randomly given 0 or 1. It's like a bit flip. You get no information more than a bit flip. So if that is the scenario, then the expectation value, you can do a simple calculation and see that in this kind of scenario where the noise is pretty high, that means the circuit is pretty deep, the expectation value tends to 0. Now, if the expectation value of the original circuit is already close to 0, then as you increase the depth of, as you fold the circuit, it is going from 0 to 0. So that means it is impossible to do a curve fitting. So if you cannot do a curve fitting, then zero noise extrapolation fails. So this is one portion. If the original circuit's expectation value is already close to 0, and as you do more folding, the expectation value goes towards 0, then there is actually not sufficient deviation in the score to do a proper curve fitting. So this is where this fails. Now, there is a simple issue with digital ZNE as we discussed. I will stick to partial folding because we want to go to bigger and deeper circuits. So I'll stick to partial folding. Now, when you do partial folding, say, take this example, I said you take 2 out of 10 gates randomly. So let's say you do your experiment and then you saw some results, you give it to me. Maybe when you chose 2 out of 10 gates, you chose this gate, you chose this gate. Both of them are pretty good in terms of noise. When I chose randomly, it ended up having this gate and this gate. So this have way more error than what you saw. So my result will be worse than what your result is. And then I will go and tell you that, no, you said the results are good enough. See, I ran with your circuit or all your parameters and it is not working. So this is one issue with this kind of partial folding. So in order to avoid that, I won't go into the deep depth of this. In order to avoid that, what is done is something called probabilistic error amplification. The idea is instead of kind of say folding random gates, say you choose this gate to fold and this gate to fold, I choose this gate and this gate, things can go different in these two cases as we just discussed. What we will do is we will identify the 2-qubit layers of the circuit, unique 2-qubit layers. In this circuit, there are only 2 unique layers. Then I will learn the noise of these layers. So once I learn the noise of this layer, and when the learning is over a layer, what is happening is, say this gate is very good, this gate is very bad. This is mediocre, this is very good. Say something like this. So the problem that if you select this and this versus if you select this and this, these two won't give the same type of result. So that your result may not be reproducible. But when we look into the entire layer, good cases, bad cases, they average out. And you are left with an average description of the noise. Now, when you are left with the average description of the noise and I ask you to fold, instead of folding individual gates, we fold individual layers. And then it's the same thing. You do say lambda equal to 3. So you fold the layer 3 times and then you have different data points, you do extrapolation. It's the same thing there. So this is why probabilistic error amplification, when you want to go to utility scale papers, 100 qubit papers, this is one of the most beautiful error mitigation technique and extremely useful error mitigation technique that you can use. The idea is very simple. You need certain data points and then you need to fit a curve and extrapolate. How do you find the data points? You need to increase the noise in the system. How do you increase the noise in the system? You can repeat gates, but the problem with repeating gates is that the choice of gate will lead to different types of outcome, because you can choose a good gate, I can choose a bad gate, and so on. So instead of choosing gates, let's look into layers, average out the effect of good and bad gates, and repeat layers. But as we repeat the layers. So this is lambda equal to 3. Say you do lambda equal to 5, or you do partial folding lambda equal to 1.2, whatever you do, you repeat the layers, you get the data points, then you extrapolate. The idea is the same. So yeah, let me again stop here, and if there are questions, we will either move to twirling next. So if there are questions, we can take those. Somehow I'm unable to stop sharing. Yeah, if there are.
No, sir, there is no question in the chat box.
Okay.
So I think you can carry on. Participants, do you have any question? No, I have checked in the chat box. There is no question posted. So
Okay, sure. So then we can
Thank you.
move on. There is a basic assumption of this zero noise extrapolation that I kind of didn't tell you. I kind of avoided telling you at this point. The question here is, sorry, just a minute. Yeah, the assumption here is that when you are saying that I am increasing the noise in the circuit, as you stretch your circuit, like the digital ZNE kind of thing that we discussed, as you stretch your circuit like that, the nature of the noise remains the same. This is an assumption that that we kind of made, and I kind of avoided telling you about this. Is this assumption a valid assumption? Let's do. And you can understand that this is, of course, not a very valid assumption. Otherwise, I wouldn't have pointed it out. So depolarization noise model, T1, T2, all of them have exponential decay nature. Now, when you have an exponential decay nature, it is still fine. Like the nature of the noise is same, although there is already a problem here that the decay rate of this type of noise, this type of noise, this type of noise, they may not be the same. You can still argue that, okay, even if the decay rates are not same, since all of them are exponential, I'll take an average of them and I'll take the average decay. Okay. That is an argument that you can still make. But there is something called an coherent over-rotation. What is that? The idea is that, you know, any quantum gate is essentially a rotation. It's a unitary, so that means it's a rotation on the unit vector space. Now, over-rotation is that you ask me that, okay, you have the quantum state rotated by some angle theta, and I end up rotating by some theta plus delta theta. This happens in a quantum computer, and this is called the coherent over-rotation kind of thing. Now imagine, yeah, I should have a picture. Maybe I want to perhaps add this kind of picture. Imagine what will happen. So you are supposed to do, let's say that you have a quantum state that you want to reach, but because you kind of did an over rotation, you missed the state. You over rotated. You have missed the state. Now you are, say your circuit has many such gates, and each of those gates has coherent over rotation. Every time you are missing, that means you are moving away from the actual state more and more every time. But remember, as we said, it's a rotation. So when you move away more and more, at some point, you are coming back towards that state. So initially, as your quantum gates start having over rotation, you are moving away from the desired state. But as this keeps happening more and more, you are moving away, and then you are rotating back, and now you are coming closer to your actual state. So it's a periodic kind of nature. It's a periodic nature where you move away from your desired state and then you again come back, you again move away, again come back. So this is the kind of periodic nature that we end up having. And this is what causes a problem. Previously, everything that we said was T1, T2, so each of them are exponential, and now suddenly I have a periodic nature curve. We need to have a single nature of noise model. Otherwise, when I say that I am increasing the noise, it gets all messed up. Some increase is exponential, some increase is periodic, then everything gets messed up. So the method to do that, to take any different type of noise model that you have and change them into this stochastic Pauli error is called twirling. So what is it? Let's say that G is a quantum gate and it's a Clifford gate. So what is a Clifford gate? By definition, a Clifford gate is any gate where, say, if P is a Pauli, and if you take the P and you put it here, it will still remain a Pauli. It may not be the same Clifford gate, same Pauli gate, but if you take a Pauli from here to here, it still remains a Pauli. For example, let's look into this. So for example, this kind of thing doesn't happen for non-Clifford gates in general. I mean, not in general. The definition of non-Clifford gate is you cannot take a Pauli and you change it and it will still remain a Pauli. Here is an example. Let's say you have a C0 gate. Now, when you apply a Z here, the Z on the target, this is the control, this is the target of C0. The Z from target actually flows to both the target and the control. So if you have a Z here, say you don't have anything here, it is equivalent to saying that you have a Z here and a Z here. So what it means, again, Z on the control only remains on the control. So what is happening here, if I put ZZ in front of C0 and if I put IZ after C0, these two things are functionally equivalent. So if I put ZZ before C0 and if I put IZ after C0, these two are functionally equivalent. But so what it means, if I put both ZZ before C0 and IZ after C0, this is exactly equal to C0. Nothing has changed. This thing then is exactly equal to C0. Nothing has changed. And this is not the only example that can happen. There are so many examples that can happen. So in twirling, what is done is we sample these Paulis randomly from the group of all Paulis. Once I have the P, I can calculate the P prime given a G. I can calculate P prime. Then I will replace G with PG P prime. And these two are functionally equivalent. So if I do this, and if I take the average over many such randomizations, and then I look into the average behavior of that channel, then we have all these depolarizing T1, T2, coherent Pauli, coherent rotation, all of these type of noise. But if we do this twirling, this is called Pauli twirling. If we do this twirling, we end up having an average channel which looks like a stochastic Pauli channel. So if you don't remember the stochastic Pauli channel, this was the stochastic Pauli channel. What it says is that with probability 1 minus P, the state remains unchanged. And then with probability P, there is an error. The error can be broken down into X gate, Y gate, and Z gate. So what it means, and here also we argued that if there are n gates, this probability becomes 1 minus P to the power n. So it becomes an exponential kind of decay. So irrespective of the type of noise that you have, the final noise becomes exponential in nature. And we end up having only a single type of noise model. in practice, once more, when we do twirling, so you can have one issue here. How many Pauli gates are there? 4, I, X, Y, Z. So if there are n qubits, how many possible Paulis? 4 to the power n. So if you want to do an sampling, you want to execute this circuit. How many circuits do you have to execute? Maybe thousands. So that's a lot of overhead. You can say that this is a lot of overhead. So how do you expect to do thousands instead of one? Well, so what is done in Qiskit is that the twirling is performed over shots. Remember, this is how we started, that you cannot run the circuit only one times. You need to run it n times. Only then you get a probability distribution, and then you can calculate expectation values or whatever. So when you run that n times, instead of having n exactly same circuit. So instead of having n circuits which are all C naughts, we will have n circuits, each of which are this randomly twirled. And then we will take the average. Again, in practice, so there is actually no extra overhead. There is no extra overhead of twirling in Qiskit. Again, just like in ZNE, here also twirling is performed only over 2 qubit gates. It's kind of assumed that the single qubit gates are noiseless compared to 2 qubit gates. And here is an example from one of the papers that I worked on, how much twirling is important. So this was something called an MBL circuit, many body localization circuit, whose, as the depth increases, the green curve shows the ideal expectation value. Now, if I don't do any error mitigation or anything, I end up with this black curve. And you are seeing that as the depth increases, we are kind of deviating from the ideal value. And that is happening because of noise. Now, if I do zero noise extrapolation without any twirling, this is what I get, the purple curve. And you can see this periodic nature actually appearing, this periodic nature that I was talking of about the coherent rotation. Some part of the periodic nature is actually coming here. And you would not be wrong if you say that this purple curve is actually a worse estimate of the ideal expectation value than even the noisy one. I mean, I would rather stick with this noisy value than this whatever stupid curve that we are seeing here. But the moment we do twirling, we end up having this blue curve, which, as you can see, is actually a much better estimate of the ideal value than the noisy value. So you can see how much twirling helps here. Let's not go into more details of this. And yeah, once more, if there are questions, we can stop and take some questions. We want to go to measurement error mitigation after this.
Yes, there is one question from Surjodip Sarkar. What is Indian position in quantum?
Okay, yeah, that's actually an important question, but let's take this at the end. We will look into, I mean, I do want to talk about India's position and what we can do, where we stand and everything. Okay, yeah. Let's just go with this last point on measurement error mitigation. So as we said, measurement error mitigation is very simple. What is measurement error? Measurement error is something that we have already learned classically. The outcomes can be either 0 or 1. And with probability 1 minus p, the 0 or the 1 remains unchanged. And with probability p, 0 is flipped to 1, 1 is flipped to 0. So this is called the binary symmetric channel. However, in general, in quantum, the channel does not remain symmetric. Why? Because there is something called this T1 error. So if I prepare a qubit in the state 1, leave it idle for some time t, and then I measure it, I don't apply any gate or anything. This is something we have actually studied back in 11-12, the Bohr's model, that it goes from one orbital down to the other orbital. There is a spontaneous emission of energy. That this is precisely what it is. That when we prepare the qubit in state 1, that means a higher energy state. If I leave it idle for some times, it has a probability that it will emit the extra energy and it will come down to the ground state. And the more we leave it, the higher is the probability. The probability of getting the correct outcome actually decays exponentially. Now, if we look into this 127 qubit Eagle processor, single qubit gate roughly requires 60 nanoseconds. 2-qubit gate requires 533 nanoseconds. Measurement requires 1200 nanoseconds. So already 2-qubit gate is almost 10 times of the single qubit gate, and this is almost twice or even more of 2-qubit gates. So if I just think that when I am measuring, what is the probability that it has decayed? Well, the probability is not non-negligible. The probability is something that we have to consider. So the probability is say 0.01 that it has already decayed during the measurement. It's not non-negligible. So say the outcome was actually 1, it was actually 0. I kind of read it as 1. This is the measurement noise, and 0 to 1 transition is affected only by measurement noise, how perfect our measurement device is. But when we think of 1 to 0, it is affected by both measurement noise and the decay coming from T1. So in general, the probability that if I have 1, I end up writing 0 is higher than the probability of 1 given 0. So the channel is not symmetric. If we make the assumption that the channel is symmetric, this is a strong assumption. So what we do is something called measurement twirling. If you remember again what twirling was, I was replacing a gate G with PG P prime such that these two are functionally equivalent. So when I measure a quantum state, what happens? The outcome becomes either 0 or 1. Now, if I apply an X gate before the measurement, if the actual state was supposed to be 1, forget about noise at this moment. If the actual state was supposed to be 1, I have changed it to 0. If the actual state was 0, I have changed it to 1. So my measurement is exactly opposite of what it should have been. So I can correct that exact opposite thing that is there by applying a classical NOT gate. It's kind of saying that, okay, I'll just if I read 1 here, I'll say, no, it was not 1, it was actually 0 because I have flipped the qubit here. So 1 is actually 0. So this is the same as PGP prime, X measurement not. So this and this, they are equivalent. So what is done in measurement twirling is, first, we just take the empty circuit. No, I mean, we just take the empty circuit, nothing gates or anything. We just do this measurement twirling. What happens when we do measurement twirling? See, we already said that the probability of going from 1 to 0 is higher than 0 to 1. Now say the state was actually 1 here, but I forcefully flip it to 0. So the probability of readout error is lowered. On the other hand, if this would have been 0, I sometimes flip it to 1. So the probability of error actually increases. So when I do this randomly again, many times, sometimes the probability of error is slightly increased. Sometimes the probability of error is slightly decreased. And then we take an average of all of it. This increase and decrease kind of cancel out. And we end up with a symmetric channel. It removes the asymmetry in probability of 0 given 1 and 1 given 0. Again, let's skip this question. So what is done in this beautiful protocol that is called twirled readout error extinction, in short TREX? What is done here? First, we just we won't go into the maths of this, but let's get the insight of what is happening here. First, I will just take the empty circuit, twirl, and I will check the outcome. since it's an empty circuit, the qubit was prepared in 0, the outcome should be 0, irrespective of if I twirl or not, because twirling is functionally equivalent to not twirling. But because there is noise in measurement, sometimes we get 0, sometimes we get 1. And when we calculate the expectation value, this actually creates a scaling of the, this error actually scales the expectation value. So here is one example where the ideal expectation value should have been 1, but because of measurement error, it changed to 1/3. So I know that 1 goes to 1/3. That means there is a scaling of 1/3. The scaling rate is 1/3. After knowing this information, what we do is we take the original circuit. This, say, U is the actual circuit that I am interested in. I twirl my measurement as before, and then I run this out circuit. Again, remember, for this case, I am not worried about the noise in gates. I am only worried about the noise in measurement. So I take the gate circuit, I twirl the measurement, and I calculate the expectation value. Now, of course, I get some incorrect expectation value because there is noise in the measurement. How much is the incorrectness? How much is the scaling that comes from the measurement noise? That we already calculated before. That the scaling is 1/3. So what we do eventually, we get the actual expectation value, the noisy expectation value that we obtained, we divide it with the scaling factor, and we can retrieve the actual expectation value that happened. Now, you can say that, look, I didn't go through this example, but if you look through this example, you can say, no, you just took a case where this worked out so well. Of course, I am just taking only 6 short examples here. When you take hundreds of thousands of shots, the average works out very well, and T-Rex is extremely powerful. It can actually correct even, say, 98% or more of this measurement noise. Now, one question or one thing that you may be thinking in your mind that, it's a lot of things that you just discussed. So what we need to do, first we transpile the circuit. Next, we want to do zero noise extrapolation. So we amplify the noise. So λ1, λ2, all of those. Then we need to calibrate the readouts. So calibration of readouts is this part where we just run the empty circuit to calculate the scaling factor. So next we have to calibrate the readouts. Then we twirl the circuit. Now we execute the circuit. Then we will have to aggregate all the twirls and take an average, because then only the average case becomes a stochastic Pauli noise model. Now I calculate expectation value. Now I need to mitigate readout error by dividing by the scaling factor. Then I need to extrapolate to zero noise. So that's a lot of things that you need to do. And if I need to take care of all of those, that's difficult. And I agree, if you say so, that it's difficult because you are interested in some of your applications, whatever you are interested in. And on top of that, if you have to keep in mind all of those things, then it becomes very difficult. So the Qiskit is to the rescue. What we have here is, when you use Qiskit, you can just do a resilience level. And if you do resilience level 0, it means no mitigation. If you do resilience level 1, it is only readout error mitigation. If you do resilience level 2, it is both zero noise extrapolation and readout error mitigation. So you don't have to worry about doing all of these things manually. You can just set the resilience level and it will take care of you, of all the things that we discussed over this talk. So just before ending and taking questions, let me just share and show this one small thing to you. Your one-stop for anything related to IBM Quantum is this website, this quantum.cloud.ibm.com. And here you can sign in. And if you have a free account, or create a free account if you don't have one, you get 10 minutes. And when I say 10 minutes, just trust me that 10 minutes is a lot. Just give it a try. I mean, many People come and tell me that, oh, what will I do in 10 minutes? I have a friend who completed one entire project of her PhD on 10 minutes. Not only that, there was another student I am working with from IISc who also completed his master's thesis on 10 minutes. So 10 minutes is already a lot. So just give it a try. And here you can see why I am saying 10 minutes a lot. See the time it takes. Quantum computing is fast. See the amount of time it takes to run the circuits. Yes, of course, when you are going towards really big circuit, that's where the goal should be, going to those big circuits, that where you need more access than 10 minutes. But to get started, to get your hands dirty, get comfortable with this kind of things, 10 minutes is sufficient. Make good use of those 10 minutes. Next, in this, you see, we have a lot of things, this learning. In this learning, as you can see, there are a lot of courses. They are divided into foundational courses, focus topic. Say if you are just starting, you can go into basics of quantum information, fundamental quantum algorithms, error correction, all of these. If you already know these kind of things and you want to go beyond, you have this focus topics like machine learning, variational algorithm, VQE, diagonalization methods, and all of those things. If you are planning to use quantum computing and show people on, show your students in classroom, there are this Qiskit in classroom. This is mainly for physics. This is mainly for computer science. You can use these notebooks. You can use the explanations that are given here. All of these that I'm showing here are free. There are no charges for any of these. If you feel like that, okay, I don't want to do an entire course, or I know these things already, just I need to check a few things out, I don't want to do an entire course, you have the tutorials here. Go into these tutorials. These are some of the best tutorials you will get for many advanced level things. And you will see these are kind of divided into several kind of stuffs here. And you will find tutorials on error mitigation here. So if you go to this, you will see all the things that we discussed today. You will see how to use that using Qiskit. And let's go to this. As you can see, the way we discussed, you can create this resilience level is there that you can set, or what they have done here. If you want more control over what you are doing, you can manually set that, okay, I am going to do measurement error mitigation. You manually set it to true. I am going to do twirling. You manually set it to true. I am going to do ZNE. You manually set it to true. Or if you don't want to do all these things manually, as I shown, resilience level 0 means no mitigation. Resilience level 1 means measurement error mitigation. Resilience level 2 means measurement error mitigation and zero noise extrapolation. So if that is what you are looking for, you don't need this entire thing. You don't need, just change here. Instead of resilience level 0, make it 1 or make it 2 as per your need. So that's where I can stop for today. I hope this was useful, and please go and use this. There was one question, and that was actually a very important question, that what is India's position in quantum computing? So the way we see, India has some of the best theoretical groups in the world. They really do. We really do. India has some of the best theoretical groups in the world. Where we are lagging, and let's be very honest, where we are lagging is coding expertise. So either people from students from physics or others, they know the theory very well, they don't know how to implement it, or students from computer science backgrounds and others who know how to implement things, they don't know the theory well. So this kind of scenario is happening here. We need to somehow overcome this. Unless we overcome this, we are lagging behind. All the utility scale papers, the 2 slides I showed, there is only one paper from India, and that comes from my paper from IBM. So there is only one paper from India, and that also is coming from IBM. But I showed you so many papers from India. So this is where we are lagging. My hope is with the National Quantum Mission, there are many good proposals that have been submitted. I hope many good of them will be funded. As you perhaps know that these proposals will have an industry application. So it is important to look beyond theory only. Theory is important. I agree. I totally agree. Understanding the theory, doing fundamental research is important. But at the same time, unless there is application-based research, it's difficult. It's very difficult to cope up with where internationally the scenario is. IBM Quantum System is coming to India next year in the first quarter in Amaravati. This I'm sure you all know. And tied up to that is the National Quantum Mission that is coming. We already have the 4 quantum hubs. The quantum algorithm call was there a few days back, maybe a month back. Those are getting evaluated by DST, and I'm sure many brilliant proposals have been submitted there. As for some of them I have heard of, and I'm expecting a lot of good work coming out of there. And just one small thing I want to show, since this question came up about the position of India, and all of you are faculties, you will go back to your students and all. As I said, just sorry, excuse me for showing this thing. As I said, you know that we are lagging in the development part, and the entire community, not just IBM. I can speak for IBM, but not only IBM. People are moving away. If you just say that I understand the theory, I understand the maths, I need someone else to do the coding for me, or vice versa. I can do the coding, I don't understand the theory or anything that goes. So with NQM, what we are hoping, the research part is going to be taken care of by the National Quantum Mission. So as I said, India already has some of the best research groups. They are tying up with the industry, and we have some brilliant proposals. There has been a lot of effort on this workforce development, like all these ATAL FDPs that are ongoing. There are many faculty development programs ongoing with this MNIT, the effort to write a book, create a minor in quantum computing. Some hackathon was recently created in Amaravati. What we are lagging is the industry readiness. And for that, and as you can see, like this happened last week, IEEE Quantum Week 2025, and the keynote address by Jay Gambetta, who is the VP of IBM, the keynote address that they gave is the software for the era of quantum advantage. So you can understand how important software is becoming. And he made some comments as powerful as this, that a quantum computer is just a paperweight without performant classical software. An application user is not expected to come and start working at a very low level. They need performant classical software. So this is where we are lagging. And that's why from the Indian IBM team, we are kind of giving a call that don't just develop. What we are planning here is whatever you are doing, have a development part to it. If you are a beginner, if you are just starting to begin, there is Qiskit Air, which does the simulation. I am sure all of you are using it, the air simulator, the noisy simulation. Don't just use it. Look into the issues, ask your students, encourage your students, look into the issues. What are the issues that are there? Try to solve one or two of them, create a pull request. If you are already a proficient, quite advanced in quantum computing, there are certain things called Qiskit add-ons, and just go and do the same thing there. And Qiskit ecosystem, if you are doing some application, there are many such repositories in this Qiskit ecosystem. Go and just contribute to something. If you find that what you are doing, no repository exists there, come up to us from the Indian IBM team. We will help you set up a repository here. But this type of involvement needs to come. You need to solve some existing issues, submit PRs. This is the step one. Step 2, enhance the software with new features. So this is just a beginner kind of thing, beginner development. This is where you need to understand the underlying quantum part. And this is where you need to understand the software, the lagging parts of software, what makes the software and the quantum theory connect with each other better. Understand those, enhance those with new features. And beyond this is make algorithmic improvements. Whatever you are doing, encourage your students to do this. Whatever you are doing, do this, do this kind of developments. Why am I putting so much effort in this? Is because two things you can do. If you are going to do, you can definitely start by yourself. I mean, if you are just submitting issues or submitting just small PRs, of course, should do this yourself. But when you are going towards more advanced things like enhancing the software, making some algorithmic improvements both to the software or adding some new research. Say you read some other paper, beginning, you read someone's paper and you see that, okay, these softwares don't have that implemented. Go and create an issue, submit a PR, implement that. Or if you are even more advanced, you have done your own research, go and do the same thing, submit a PR on that. At this point, you should reach out to us if you need help. You are more than welcome to do it yourself if your students want to. If not, reach out to us. We are very happy to help you or connect you to the right people who can help you. If you make a significant contribution here, we have something called this GRM, called Global Remote Mentorship. If you make a significant contribution here, not just solving a simple PR or something, but if you do something at this level or this level, we are very happy to give you some GRM certificates. This is kind of an online remote mentorship. We are very happy to give you a certificate for that, for whatever involvement we have with you. We are even trying, I have not written here because it's not worked out yet properly, but we are trying our best that when you are submitting some PRs or doing some sort of engagements here, we try to provide you with batches that you can go and show in your CV that you have done something. But this is also what makes you showcase your proficiency in quantum computing and software development. So many students reach out to us and ask that, okay, what is required for internships or jobs? This is what is required. You need to understand the theory. You need to be able to do the software development. Either or is not an option. It's both. And how do you show us that you know the theory? Well, you have taken some courses or something. How do you show us you know actual coding and software development via one or more of those? Not by saying that, okay, I have done something. Then it becomes very difficult for us to also recognize what you have done, what the students have done. So by some of those things, we are also planning to use this as a method to screen the students. So this is actually a call that we are giving out. And interestingly, we are planning to give this out next week, actually. So you are kind of the first guys I spoke about this one. But please encourage your students if they are interested in pursuing a career in quantum computing, the way the industry is moving, you need to have this motto. You cannot just say that, okay, I have done some very small things and I have just written a small code in Qiskit, run a few 5-qubit algorithm and I have submitted a paper. Everyone is doing this. If you want to stand out, show that you have the capability, you know the theory, you know the latest techniques, you know how to use them, you are going to something beyond 30 qubits, you have the capability to do those, and you have the capability of software development. So this is something that is very, very important. And I really ask you, please go and ask your students to take this up seriously. This is going to be the way we kind of decide skill sets for internships and job applications. So yeah, sorry, I kind of diverted from error mitigation, but this was a good opportunity to tell you about all of this. So thanks a lot for your attention and listening to me.
Thank you. Thank you so much, Dr. Majumdar. Your last few slides were really, I think, will be helpful for all the faculty members who are present over here, because we belong to different organization, and this information, I think, will be helpful for all the organizations. We must uh, we must say our students about this. Apart from the knowledge you have shared about the quantum computing,
So can you
participants.
please, can you please give us the URL in the chat section that where should we register to use this facility?
Sorry.
Sir, can you please put the URL in the chat section?
Sure. So just give me a second. So this URL that I gave here in chat, the Qiskit community, here there are many repositories. So as I was saying, that whenever your students are doing something, just encourage them to say they have done something in machine learning, something in optimization, physics, chemistry, biology, anything. There are repositories existing. So go and solve some issues of those repositories, or if you have done something novel, just go and upload that, submit it as an issue to that repository. That becomes public, and then you can actually showcase that, okay, I have done this work and this is the code which is already available. If it turns out that you have done something whose repository doesn't exist, reach out to someone from the IBM quantum team. Will help you set up a repository for that.
Participants, do you have any questions? Someone is trying to connect to the audio. So, is it that you have any question, sir?
Probably make a quick observation. I was at Urbana Champaign probably about 3 years back. So what I found there were the University of Chicago ecosystem, right? They got together all the institutes and everything, and they were already in a position to create hybrid qubits, right? Some super, some super cooled, and quite a few at relatively higher temperatures. So this kind of an ecosystem where university in the US, we do see that university ecosystems have come together and built out the hardware as well, right? Are we seeing anything similar in the India quantum mission, or is the emphasis right now?
Yes, and I think that has been a major emphasis of National Quantum Mission, is to bring institutes together. One of the requirements that was given in those applications for National Quantum Mission is that if you apply as a single PI, or even if you apply only, say, 2 or 3 people from your same institute, you will directly be rejected. This was more or less an unofficial thing that was announced. So I haven't followed the hardware or those parts very closely, but the algorithm parts that I have followed, and I have been very happy to see many institutes coming together with industries, with government organizations and everything. So at least the National Quantum Mission is definitely trying to drive that ecosystem. I hope that sustains.
Excellent, excellent. Thank you. Thank you so much. Wonderful presentation again.
Thank you.
Is there any other question? Participants, or we can wrap up this session. I think we can say thank you to Dr. Majumdar because already time is over and I don't think participants have any more questions.
Sure, thanks a
Shuma
lot.
madam, Shuma madam, are you there?
Yes,
Okay, so shall we
yes,
proceed to the next
yes,
session?
yes. Atanu
Thank
sir
you.
has already joined.
Yeah, yeah. So thank you once again, Dr. Majumdar.
Thank you.
And
Maybe
And
we
on
should,
behalf-
we should give the participants
Yes.
a little bit of a breather, just to absorb and reflect what Ritajit said. And quite, he was very forceful in his emphasis that we, what does building systems really come from? So I think we should just give it a few minutes for people to absorb what's been told.
Okay, okay, thank you, Mr. Rajchaudhuri. Thank you for your nice suggestion. So as sir has suggested, can we take a quick break of 2-3 minutes? Then we will start the next session, maybe at 3:40. Is it okay,
Sounds
Shuma
good.
madam?
Is it fine, Shoma ma'am? Atanu sir, with your permission, can I stop the screen recording for 1 or 2 minutes?
Absolutely, absolutely.
Yeah. Thank you.
Go right ahead. We will
Yes.
start at 3:40 then.
Okay.